In this video, we're going to spend a lot of time talking about the angles of a circle. And inside a circle, outside a circle, all kinds of angles. Let's start with something familiar, the central angle of a circle. If I can get this up. The central angle of a circle, right, that's here and here. It's formed by the radii, by two radii and the center of a circle. We know that, I don't know, sure, A, B, C. We know that the measure of angle ABC is equal to the measure of arc AC, right? That's central angles. Pretty self-explanatory. Okay, inscribed angles. So this angle now, so the vertex of this angle was on the center of the circle. Now this vertex is on the circle. So we could do this, oops, here, here. Okay, now, if this was A and this was B and this was C, for inscribed angles, the measure of the angle, measure of angle ABC, that's equal to half the measure of the inscribed arc. So for inscribed angles, the measure of the angle is half the measure of the inscribed arc. Okay, and again, this is an angle that's on, the vertex is on the outside of the circle. Okay, for chord angles, this is where the vertex is inside the circle. So let me see if I can do this. Something like that, maybe. I don't know. And we'll call this F. Why not? Okay. Guess I could have called it E. Sure. So we have all of this. Now, how do these relate to each other? Well, the measure of angle AED, because remember, these two angles are congruent to each other. So this would also be the measure of angle CEB. That's equal to the average of the arc lengths. So that's equal to AD plus CB divided by 2. So the average of these arc lengths is equal to the measure of the angle. And you could do the same like AC plus this big DB right here. That would be equal to DEB. So for chord angles, the angle is equal to the average of the arc lengths. Now let's talk about chord tangent angles. I guess I can leave that right here. Chord tangent angles. Where the vertex is at the point of tangency, right? So let's see. We could draw it like this. So I have a line. Oops. Sorry, this is taking me a second. A line like right here. And a chord that goes through the circle. Like that. Okay, we could call this A. Sure. A, and let's call this B. And then I'll put another point here, C. just so that we're talking about a minor arc here. Now, I'm going to go ahead and number these angles because it'll be easier to talk about since I don't have more points. So that's angle 1. Man, let's just do this. Sorry, I'm kind of indecisive. So let's call this D and let's call this E. Okay, just so that you have a very, very clear picture of what's going on here. Now the measure of angle DAB is equal to half the length of arc AB. In the same way, the measure of angle BAE is equal to half the length of arc ACB. Okay? So this angle here is half of that arc length. So if arc AB was 100, then this measure DAB would be 50. And that makes sense, right? Because these two angles, DAB plus BAE, they add to 180, right? They're supplementary. And the two arcs, AB plus ACB, those add to 360. So it would make sense that those two angles are half, or those angles are half the arc lengths. Okay, what if we have a secant line and a tangent line? So remember, a tangent line, like we just had here, I can make that solid in just a second. Tangent line. And then maybe I actually want this probably more. Like that. So a tangent line and a secant line, they have the same. All right, we're just going to redo this. Okay. We've got this. We've got that. Okay, so here's my tangent line. Here. That line is tangent. Really a tangent ray, right? And then here is my secant line going all the way through here. Okay. So now we have A and B and C. Okay, the measure, and then let's call this, I don't know, D, why not? The measure of ADB, of that angle, is equal to the, and I don't know, well, it's fine. It's equal to arc A, the measure of arc AC minus arc BC divided by 2. Okay, it's equal to the difference divided by 2. And really, if we were to generalize this, we would say that this is the big arc minus the small arc divided by 2, right? That's that angle. ADB is the big arc minus the small arc divided by 2. That's what the angle is equal to. Okay, this is a tangent and a secant where your vertex is outside of the circle. And it's not the average, right? It's the big arc minus the small arc divided by 2. Okay, our last kind of circle thing is for tangent lines specifically. It only works for tangent lines. So here we have tangent line. Keep them the same color because they're the same kind of line. A, and we'll call this B, and we'll call this C, and we'll even put a point D here. So let's say we need to think about this, right? Because this is very, very similar. It's actually the same as tangent secant, right? The measure of angle ABC is equal to the big ADC minus the small AC divided by 2. Now, there's a difference here with tangent. What's the difference? Well, I know that AC plus ADC is 360, right? So I could say that arc ADC, right, that's equal to 360 minus arc AC, right? Because AC plus ADC is 360. So ADC, I can represent it as 360 minus AC. Okay. So then how does that change this equation? Well, instead of ADC, I would write 360. Maybe I can write it in orange. 360 minus the measure of arc AC, minus the measure of arc, oops. Changing colors is hard. Minus arc AC again, right? I just replaced ADC with 360 minus AC divided by 2. Okay, so then that equals 360 minus twice AC divided by 2. And if you divide everything by 2, 360 divided by 2 is 180. 2AC divided by 2 is just AC. So the measure of angle ABC is equal to 180 minus the measure of arc AC. Okay, what does that mean? Well, it means that that angle and that arc are supplementary, which is kind of cool. So it's not necessarily that you have to memorize this, but this is kind of a helpful trick to have up your sleeve. It might save you a little bit of time. So, and you only need to know this arc right here, AC. Now, again, you could figure it out that this and this add to 360, right? AC and ADC add to 360. So you can figure it all out. But this is helpful. It makes it maybe a little bit quicker for you. Okay, just a couple of theorems that I wanted to talk about before we finish up these notes. If I can. Maybe. Okay, there we go. Circle. An inscribed triangle with one side length the diameter is a right triangle. So let's get a circle. There we go, sure. And the diameter of the circle. Oops, that was a pretty good line actually. I'm not mad about that. The diameter of the circle. Okay. An inscribed triangle with one side length the diameter. Inscribed, if you remember back to our first set of notes, inscribed means that all of the vertices are on the circle. So we would have this, oh man, oops. We'd have the triangle here, and it doesn't matter actually. It just has to be inscribed. Is a right triangle. Now, how can we prove that? I know that an inscribed angle is half of the length of the intercepted arc, right? So A, B, C. I know that the measure of angle ABC is equal to 1/2 of AC. Now, AC is half the circle, right? And that length is half the circle. So I know that arc AC is 180. So that means that the measure of ABC is 1/2 of 180, which is 90. Okay, so that means no matter what, it's a right triangle. And you could draw that as long as it's intercepted. You could draw any number of right triangles, right? You could draw a right triangle here. You could draw a right triangle here. right? Any of these, even like here is a right triangle. No matter what, all of these are right triangles, no matter where you draw it. Because the intercepted arc is always 180. So, I don't know, that's kind of cool. And it looks nice too, right? That's the most important part. Let's look at our second theorem. For a quadrilateral inscribed in a circle, opposite angles are supplementary. Okay, so let's get another circle. And just any quadrilateral, right? It actually doesn't matter what the quadrilateral is. So let's try to make it. I always have a hard time making this not look like anything, but I think that'll be pretty good. Kind of looks like a kite, but that's fine. So, okay, let's think about this. Why would this work? Well, if I call this A, B, C, D, let's just think about what we know. I know that the measure of angle ABC is equal to 1/2 the length of arc, CDA, right? This angle, that's half this arc because it's an inscribed angle. I know the same for the opposite, right? I know that the measure of angle CDA is equal to half the measure of arc ABC. Right, and we're just looking at opposite angles, so let's focus on this. Okay, what else do I know? Well, I know that arc ABC plus arc CDA, that's the whole circle, right? ABC and CDA, that's the whole circle. So that's 360. Right, and I can do kind of like what I did with the tangent. What if I said that the, how can I say this? Well, I know that those equal 360, right? So then oh, I know. I think. Okay, well, let's just try. Let's do a little bit of substitution. So the measure of arc ABC is equal to half arc CDA, not CDA, sorry, arc ABC. Oh, sorry. So here, CDA equals 360 minus ABC, right? Okay, so then this is 360 minus ABC. Okay, now we're getting somewhere. So then the measure of arc A, or of angle ABC, is equal to half of this, so that's 180 minus 1/2 ABC. Oh, and look, CDA is 1/2 ABC, so I can just substitute that. The measure, the measure of angle ABC equals 180 minus the measure of angle CDA. And then to make it so that they're supplementary, right? That would be that the measure of ABC plus the measure of angle CDA is equal to 180. Boom, baby. That feels good. Could have done a little bit better with my colors, I'm sorry. But I think that works, right? You can say, I know that these two arcs equal 360, substitute in, solve, substitute again. Right, maybe we could be really clear. This I substituted in right here. And then we've got the two angles being supplementary. And you could do the same thing with the opposite, with the BAD angle and BCD angle. Okay, that's it. So a lot to take in for sure. This is a really helpful reference sheet to have. And I think as you solve more problems and do more work, you'll become more and more familiar with all of these different properties for the angles of a circle. Thanks for bearing with me. I'll see you in the next video.